Hello and welcome to one and all. My name is Premal Popat and today we'll be studying the last module, that is the module 9 of the chapter Effects of Electric Current, and this is the chapter from Science and Technology Part 1 of 10th Standard textbook. In this module, we'll be studying about the alternating current and the direct current, that is the difference between both, and also the working and construction of an electric generator. So let's proceed with the topic. What is a direct current? Now, direct current is a non-oscillatory current flowing in one direction in a circuit from cell to cell. That means this current is not oscillatory. This current can be stable and it always flow in one direction. Now in this chapter, like in the previous modules, we have studied the circuit diagram in which a battery was used. So through this battery, the direct current flows. That means the direct current is not oscillatory, it can be stable. Now this is the circuit diagram wherein the electrons move in one direction only. And here we can see the negative and positive terminals of the battery. So the electrons move from the negative to positive terminal, and this rectangular which is attached to the connecting wire is a load. So this electrons move in one direction only, and hence this current flows in one direction. So direct current may flow through a conductor such as a wire, but can also flow through semiconductors and insulators. An electrochemical cell is a prime example of DC power. Like we have studied the battery, it is nothing but a cell. And it is a electrochemical cell. So this cell is an example of DC power. Through this cell, the direct current flows. This is the graph of the direct current, that is the voltage versus time. So here we can see the red color line, that means this current can be stable at some time. So it is a non-oscillatory current flowing in one direction in a circuit from the cell to cell. The direct current can increase, can be stable, or can reduce also, but it is not oscillatory. So if we want to increase this direct current, it can increase. We can increase this current. Also we can decrease it, and also we can keep it stable. So this is all about the direct current. We just have to keep in mind that direct current is not oscillatory. It flows in one direction, and battery is an example of a DC power. What is alternating current? Alternating current is a current changing in magnitude and direction after equal intervals of time. So this is the current which changes in magnitude as well as direction after equal intervals of time. So this is the circuit diagram where we can see there are arrows shown. That means the electrons move back and forth. The direction of the current, also the magnitude, changes after equal intervals of time. The alternating current flows in a periodic manner in one cycle in forward and reverse direction. So this is the graph of the alternating current, and on the y-axis we have current in amperes, and on the x-axis we have time in seconds. So here we can see that the blue color line shows the direct current, and this graph, the orange color one, the orange color wave, we can say it is the alternating current. The direct current in this graph is stable. Now the alternating current will increase from 0. Like here on the x-axis we can see like there are reading marks as 0, 0.5, 1, 1.5 amperes and so on. And also on x-axis The time is shown, that is from 0 to 0.5 to 1, 1.5 and so on. So this alternating current increases from 0. It will increase and reach the maximum. It will reach the maximum point, and then after reaching the maximum height, it will decrease and come back to 0th position. Okay. Now it will flow in other direction. That means over here below the 0 line, it will flow now. So it will increase in the opposite direction. It will reach the maximum and then again decrease. This one is known as the positive half cycle, like which I am marking in red color. This is the positive half cycle because it is flowing in the positive direction. And this one which I am marking in yellow color is the negative half cycle. Now students, here the current is not negative, the current is positive. Just to show the change in direction, we have taken the current to be negative. In both the intervals the current is positive, only just to change the direction the current over here is taken negative. So this one, the positive half cycle and the negative half cycle together clubs as one full cycle. So in this way the alternating current flows. So the oscillation of the alternating current occurs in a sinusoidal manner with time and hence is shown by the symbol. So this is known as a sine wave. The whole one cycle is known as a sine wave, and the alternating current occurs in sinusoidal manner. The alternating current is oscillatory. We can see from the graph that the alternating current increases, reach to a certain maximum and decreases, and again it will repeat the same procedure in the opposite direction. So this alternating current is not stable. It is oscillatory. It increases to a maximum, then reduces to 0, and again increases to maximum in the other direction and again is reduced to 0. So here we can say that the alternating current is oscillatory. It changes in magnitude as well as direction after equal intervals of time. And the graph of the oscillation of the alternating current is shown in a sinusoidal manner, that is shown by a sine wave. Over here the alternating current and the direct current is shown in the graphical manner. On y-axis we have current in amperes and x-axis we have time in seconds. So this is the whole sine wave which I am marking in red color. This is a sine wave, that means the alternating current. Okay. Now let us represent this alternating current in terms of direct current. So here at the start the alternating current increases. So here we can say that we are increasing the direct current, and at some point, that is when it reaches the maximum, it is stable for few seconds. So here we can make the direct current stable at this point. Now again after reaching the maximum the alternating current will reduce. So accordingly we can reduce the direct current. So students, in this way we can represent the direct current in the form of an alternating current. So first the direct current will increase, then be stable and will decrease. Applications of alternating current. So where is this AC current used? Students, in our homes we make use of appliances. So these all appliances need current. Okay. So these appliances make use of alternating current. We have a switchboard, right? So we get the current from the main power hub. Like on the screen we can see the picture how the current is transferred from this power hub, that is the current is transmitted from this power hub to our homes. So there is a procedure, right? Over here alternating current is used, and why this current is used? When the electric power is transmitted over a long distance, it is beneficial to have it in AC form as it results in minimum power loss during transmission. So during the transmission of current there is a power loss. So when we use this alternating current, the power loss is minimum, and that is why alternating current is used to transmit over long distances. And the home supply is of alternating current, the current which we get in our sockets, that is the main power board, is the alternating current. So these are the applications of alternating current. Electric generator. Let us first understand why do we use electric generator. So when there is a power cut at our homes, we make use of this generators. We have seen these generators at many places, like in schools, at our homes also, and also in shops. In the previous module, we had studied that a current was induced in a coil due to the movement in the solenoid coil. But the current induced was of very small magnitude. That means the current induced was in microamps. This current won't be enough for the appliances to work, but we can use the same principle to produce large amount of current, and this principle we are going to use in electric generators. We will understand that in previous. We will understand this in further slides. So this in electric generators, the mechanical energy used to rotate the current carrying coil in a magnetic field is converted into electrical energy. So in electric generator, the mechanical energy is converted to electrical energy. Before moving on with the generator, let us understand about how the current is induced. That is, what is electromagnetic induction? Electromagnetic induction is a process in which a conductor is put in a particular position and the magnetic field keeps varying, or the magnetic field is stationary and the conductor is moving. Either of these things, that is, the magnet or the conductor, is moving. So when this is the case, an EMF, that is electromotive force, is produced across the electrical conductor, and due to this electromotive force a current is produced. So what is this EMF? EMF is a kind of a voltage which pushes electrons from positive to negative terminal of the battery. Why from positive to negative? It is because the current, that is the conventional current, is the flow of charges from positive to negative terminal of the battery. So this EMF is a kind of a voltage, and that is why the current is induced in a coil. Construction of an electric generator. The diagram of the electric generator is somewhat same like electric motor. We can see a coil ABCD connected to the carbon brushes, and there is a ring. Also there is a galvanometer, and there are two magnetic poles, that is the north pole and the south pole. Let us understand the construction. Copper wire coil ABCD kept between the two pole pieces of a magnet. So this copper coil ABCD is kept between the two pole pieces, that is the north pole and the south pole of the magnet. The two ends of the coil are connected to the conducting rings R1 and R2 via carbon brushes. The two ends of the coil are connected to this conducting rings. There is a ring R1 which I'll mark in blue color, and there is a ring R2. Okay, so these two ends of the coil are connected to these rings R1 and R2 via carbon brushes. Here we can see the carbon brushes, and we already know that why these carbon brushes are used. So this coil is connected to R1 and R2 via the carbon brushes B1 and B2. Both the rings are fixed to the axle, but there is a resistive coating in between the ring and the axle. So these rings are connected to the axle. Now this over here is an axle, and there is a resistive coating between the ring and the axle. The axle is rotated with the help of the machine from outside. So this axle will be rotated with the help of the machine which is outside this internal circuit. Now this whole thing, the coil, the magnetic poles, the rings, this is the internal circuit of an electric generator. Now this axle will be rotated with the help of the machine from outside, and because of this the coil ABCD starts rotating, and in this way we get the mechanical energy. The stationary carbon brushes B1 and B2 are connected to a galvanometer which shows the direction of the current in the circuit. So this brushes with the help of the connecting wires are connected to a galvanometer. Now this over here is a galvanometer, and this galvanometer will detect the amount of current and also the direction of the current flowing through the circuit. So this is the construction of an electric generator. To understand the direction of the current, let us understand what is Fleming's right hand rule. What is this Fleming's right hand rule? This rule enables to know the direction of the induced current when direction of the magnetic field and the motion of conductor are known. So we will know the direction of the induced current when the direction of the magnetic field and the motion of conductor is known to us. So basically the thumb, index finger and the second finger of the right hand are stretched perpendicular to each other. All these three fingers are perpendicular to each other. The thumb will represent the motion of the conductor. The first finger represents the direction of the magnetic field, which is always from North Pole to South Pole. When these two parameters are known, the second finger represents the direction of the induced or generated current. Okay, and this induced current will be perpendicular to both, that is magnetic field and the motion of the conductor, and the direction of the induced current will be the direction of the conventional current, that is from positive terminal of the battery to negative. So in this way we will know the direction of the induced current flowing through the circuit. Working of electric generator. So on the screen we see an image of the electric generator, like what all components are there inside the electric generator. We have two magnetic poles, which is the north and the south. There is a coil ABCD which is placed between these poles. There are the conducting rings R1 and R2 and the carbon brushes B1 and B2. And there is an axle which rotates the coil from outside, and there is a galvanometer which detects the direction and amount of current flowing through the coil. So let us see what happens in this case. So according to Fleming's right hand rule, electric current is produced in the branches AB and CD in the direction A to B to C to D. So according to Fleming's right hand rule, electric current is produced in the coil. Let us see how. So now the magnetic field is from north pole of the magnet to south pole. So I will denote this by a horizontal line, and This horizontal line denotes the magnetic field, which I am representing by B. B denotes the magnetic field and it is from north pole of the magnet to south pole. Now this coil is rotated with the help of an axle from outside the electric generator, okay, from the external circuit. So this coil is rotated in clockwise direction. That means AB is going upwards and CD is going downwards, okay. So now if we consider this AB, it is moving upwards. That means the coil is rotating in clockwise direction. That means in upward direction. So this vertical line represents the movement of the coil. I am denoting it by C. So Fleming's right hand rule says that when the magnetic field and the movement of the coil, that is the direction of the movement of the coil, is known to us, then we can find out the direction of the induced current. Now in this case, the magnetic field and the movement of coil is perpendicular to each other. So we also know that the direction of the induced current is perpendicular to both, right? All these three parameters are perpendicular to each other. So that is why this current, now if we consider the right hand, okay, so B is from north pole to south pole, that means in horizontal direction. This current coil is moving upwards, okay. So because of this thing, the induced current will flow from A to B to C to D, that means perpendicular to both the magnetic field and the coil, and that is why the direction of the current is from A to B to C to D. Now this happens in the internal circuit, okay, inside the coil. Now let's see what happens when the current reaches the point D. So in the external circuit, now external circuit consists of this galvanometer, carbon brushes and connecting wires. So in the external circuit, the current flows from B2 to B1. So now the direction of the current is from A to B to C to D and it reaches B2, right? So this current flows from B2 to B1. I'm denoting this by a curve, okay, through galvanometer. So BA is always in contact with brush B1 and CD is in contact with brush B2. Now from the diagram we can see that this BA is in contact with brush B1 and CD is in contact with brush B2. It is clearly seen from the figure, and that is why when the current reaches D, it flows from B2 to B1. Okay. Now what happens after the half rotation? AB takes the place of branch CD and vice versa. Now what happens? This AB will come to the position of CD and CD will come to the position of AB. That means after 180 degree. That means after half rotation. So what happens to the induced current? The induced current goes from D to C to B to A. Now see students over here, the direction of the induced current has changed. First it was from ABCD, now it flows from DCBA. How? Let us understand. Now according to the Fleming's left hand rule, this magnetic field and the movement of the coil are perpendicular to each other, right? So that is why the current is flowing from DC to BA. So when this current flows from DC to BA, what happens to the external circuit? The current flows from B1 to B2. Now when the current reaches point A, it flows from B1 to B2. Why? Because BA is in contact with B1 through the galvanometer. So from this what can we conclude? This cycle repeats after every half rotation and alternating current is produced. Now this cycle which cycle, like after every half rotation the direction of the current is changed. Okay, and same happens with the alternating current. Like for every half rotation the direction of the sine wave or the direction of the alternating current changes, right? So this is all about working of electric generator. In the previous slide we studied about AC generator. The direction of the current was changing, right, after every half rotation. At the start of this module, we studied what is an alternating current. An alternating current is oscillatory. The direction and magnitude of the current changes after every half rotation. So in the previous slide, the electric generator, which was explained to you all, was AC electric generator. Now let us understand about DC electric generator, like what all things will we need to make DC electric generator. We know that the DC does not change the direction in the external circuit. The DC generator is not oscillatory and it flows in one direction. Also, it doesn't change its direction. So to achieve a DC electric generator, we need a split ring fixed on the axle, like the split ring used in the electric motor. Like in the previous slide, it was a full ring. There were no gaps in the ring, right? But over here we will need a split ring, and we will need only one split ring, okay, as we can see in this figure. And this split ring will be fixed on an axle, and with the help of the axle the coil will be rotated. So because of this, what happens? Because of this arrangement, the branch of the coil going upwards will always be in contact with one brush, and other branch going downwards will be in contact with the other brush. That is, the one side of the coil will be in contact with one brush and the other side of the coil will be in contact with the other brush, and due to this arrangement the current will flow only in one direction and it won't change its direction. So a split ring is used to make a DC generator. In today's module, we studied about the AC and DC current, like what is the difference between these two currents. Also, we studied the principle, construction and working of AC generator and what all components will be required to make a DC generator. So students, this was end of the chapter effects of electric current, and we have covered 9 modules in this chapter. Thank you so much everyone for your attention.